This is an LED bulb. These bulbs come with a color temperature rating. In this case, the color temperature is rated at 5,000 degrees K. That is approximately the same color temperature as sunlight. I had assumed that these color temperature readings would be accurate and reproducible for these LED bulbs. However, when working on another project, I discovered that that was not necessarily correct. This is a smartphone running a color temperature application. This app is available on the Google Play Store. I installed this color temperature application for another project. Because every smartphone is slightly different, the creator of the color temperature software recommends calibrating the software on your particular smartphone using sources of known color temperature. Since the LED bulbs have rated temperatures, I decided to use them. I measured the color temperature of two identical LED bulbs, but I got different results. I have 4 of these identical bulbs. They are all manufactured by Corey, and they're all rated at 5,000 degrees K and rated at 60 watt equivalent brightness. Each one of these bulbs has been in service for a different length of time. I measured the color temperature on all 4 of the bulbs and correlated it to the time in service. The longer the bulb had been in use, the higher the color temperature. The correct way to measure color temperature of the bulb is to have the bulb illuminate a flat sheet of white paper and measure the light reflecting from the paper. This is a little rig I set up to measure the color temperature of several different bulbs of different ages. So I have simply a white piece of paper taped to a flat surface, and I have a lamp with a bulb in it. I'm simply going to try different bulbs and measure the color temperatures and compare them to the age of the bulbs. Our first bulb is a brand new bulb. It hasn't been used, and it's been on for a few minutes. It's giving us a color temperature of 5300, 53 or 5350. Next we have a bulb with relatively few hours on it, probably no more than a few hundred, 5400, so it's slightly higher. Next is a bulb with possibly 2,000 hours on it. We're getting a color temperature of 5450. Now we have a bulb which has over 10,000 hours of use on it, and it's reading 5,800 degrees K. And as it warms up, it's creeping up a little higher now to 5,900 K. There is a slight variation in all of the bulbs when they go from cold to hot. They go up maybe 50 degrees, but there appears to be a trend to increase in color temperature as the bulb ages. What is meant by color temperature? The concept of color temperature is based on incandescence. Any object with a temperature is going to radiate energy. The frequency of the radiant energy is going to increase with temperature. Frequency is inversely proportional to wavelength, so the higher the temperature of the object, the higher the energy of the photons and the shorter the frequency of the wavelength of the light. The wavelength of these photons is usually expressed in nanometers. Nano indicates 10 to the minus 9th power. Color temperature is always expressed in terms of degrees Kelvin. Kelvin is a metric temperature scale based on Celsius. The increments of temperature in Kelvin and Celsius are the same, but the 0 degree point is different. In the Celsius temperature scale, the freezing point of water is arbitrarily set at 0 degrees. In the Kelvin temperature scale, the 0 degree point is set at absolute 0, so there are no negative temperatures in the Kelvin scale. In the Kelvin scale, the freezing point of water is 273 degrees. To convert Celsius to Kelvin, just add 273. In physics, the relationship between temperature and wavelength is described by Planck's law. The physics is very complex, and there's a great Wikipedia page on the subject if you really want to delve into the subject. But in a nutshell, it boils down to this. E equals h nu, and that is the Greek letter nu, where E is the energy of the photon, h is Planck's constant, and nu is the frequency of the light photon. This is what blackbody radiation curves look like. On the y-axis we have the radiation intensity, and on the x-axis we have the wavelength of the light. In this case, it's expressed as micrometers rather than nanometers. This range here is visible light. At the blue end we are 400 nanometers, and at the red end we are 700 nanometers. Now each one of these curves is a black body at a different temperature. Black body at 2000 degrees K, glowing very slightly in the deep red. At 3000 degrees K, we would get a much brighter red, probably more towards the orange. At 4000 degrees K, we're probably getting orange to yellow. And at 5000 degrees K, we're peaking about here. So this would look a yellowish white, and this is very similar to sunlight. Now, wavelength and frequency are inversely proportional. So as we get shorter wavelengths, we get higher frequencies and therefore higher energies as we go from right to left. And the higher the temperature of the object, the higher the peak temperature, and the frequency at which the blackbody radiation curve peaks also increases. And this black line is connecting the peaks of the blackbody radiation curves. Now, this is great if you're talking about incandescent light bulbs, but we're talking about LED light bulbs. LED light bulbs actually do not obey the blackbody radiation curve. They're not based on thermal energy. They're based on emission spectra. These are the emission spectra of three different types of LEDs: blue, green, and red. The emission spectra are very narrow. The D in LED stands for diode. And this is basically what a diode looks like. We have a P-type semiconductor and an N-type semiconductor. In between them, we have what's called a depletion layer, but there is what's called a band gap in here that has to be overcome. The band gap is the energy level between the valence band and the conduction band. So when electrons fall from the conduction band to the valence band, they give off a very specific energy level. And the wider the energy gap, the higher the energy. So a relatively narrow gap would give you a red color, a little bit wider gap would give you a green, and a very wide gap will result in a blue LED. So LEDs produce a very narrow band of frequencies and therefore a specific color. So we can manufacture red LEDs, green LEDs, and blue LEDs. But how do we make a white LED? One way to make a white LED is to combine three LEDs into one device, a red, a blue, and a green, and an observer will see this as white light. You could use phosphorescent substances which will absorb light and re-radiate them at different frequencies. Here's an example of using a blue or an ultraviolet LED in a complex mixture of phosphorescent substances which will absorb the blue or ultraviolet light and re-radiate it as a combination of reds and greens. And this could also give you a white LED. But the way it's usually done is by having a more simple phosphor which absorbs the blue light and re-radiates it as yellow. The blue light from the LED plus the yellow light from the phosphor will give a white LED. This is how a white light LED is constructed when using a blue light LED and a yellow phosphor. This is the blue light LED. It emits high energy blue light. That blue light passes through the yellow phosphor. Some of that blue light is absorbed by the yellow phosphor and then re-radiated as yellow light. And so you have a combination of blue and yellow light being emitted from the LED, and the observer perceives this as white light. Now, I don't know for certain how this particular LED bulb works, but since the blue LED plus the yellow phosphor is the cheapest, it is almost certain that that is how this bulb also works. By adjusting the mixture and concentration of the phosphors, we can produce different color temperatures. If we want a cool white 5000 degree K LED, that would be our blue line here. There's the blue LED peak, and here is our phosphor peak to the right. If we want to have a slightly warmer white LED, like 3700 degree K, a little bit more phosphor, and so the phosphor peak is higher, pushing the average color temperature a little bit to the right. And then if we want a very warm white 2600 degree K bulb, we have a lot of phosphor relative to the blue LED, shifting the temperature very significantly to the right. One of the strange ironies of color temperature is what we call warm white actually corresponds to the lowest color temperature, and cool white corresponds to a higher color temperature. Now, whether it's considered warm or cool is based on the emotional feeling it generates, whereas the color temperature in degrees Kelvin is based on the equivalent blackbody radiation curve in physics. So this all began when I was trying to figure out why the color temperature was changing as the bulb was aging. And it was a bit of a learning experience for me to learn how they actually worked. So what I think is happening is that over time, the phosphors are changing or degrading or oxidizing or something. such that the amount of light the phosphors are giving off is slowly decreasing over time. And when that happens, the blue component is going to get proportionally greater, and the color temperature is going to gradually creep higher. So that's my guess as to what is happening. Now, this is a rather small sample. I looked at only 4 bulbs. However, I have read a number of posts online where people report white lights becoming progressively bluer over time. So perhaps I'm not the only one who's observed this. So again, this is what I think is going on. I believe our white LED is constructed using a blue LED and a yellow phosphor, and the combination is giving us white, and over time the yellow phosphorescence is losing its brightness for some reason, possibly chemically degrading. Okay, thanks for watching.